Alright, so in this video we talk about P3 vectors, and vectors is one chapter you guys haven't done in Pure Math 1. So there will be some stuff that were there in the previous syllabus of Pure Math 1, and then obviously some of the P3 stuff. So basically there has been a modification in the P3 syllabus for vectors, and we'll be basically talking about this chapter in terms of the new syllabus, obviously. Now, recall that vectors um, basically refer to the distance of, or basically refers to the distance between 2 points in a given direction, right? So, for example, if I say the vector AB is denoted by a column vector 2 comma 2 5, it basically means that in order to go from A to B, the the displacement in the x direction is 2 units, the displacement in the y direction is positive 5 units. Or simply, in order to go from point A to point B, you'll have to go 2 units to the right and 5 units uh, vertically upwards, and that leads to the vector 2 5. Now this form is called the column vector form, right? Now the same thing can be denoted in a different way using the ij form, 2i plus 3j. This essentially means that in order to go from A to B, you have to go 2 units in the I direction, which is usually 1 unit in the positive x direction, and 3j, meaning 3 units in the positive j direction. So these are two formats you need to be comfortable with. Now, you've done all of this, including vector addition, subtractions, multiplications. Multiplication meaning scalar multiplication with a vector. For example, 5 times of 2 comma 3 is the vector 10 15, which is 10i plus 15j. Now these are things you've already done from your O levels, and you're expected to know all of this. Whether you have done add math or not, you're supposed to know a few of these things. Now, what you're not supposed to know, and what you'll be introduced to in this section, in this syllabus, is the third dimension of vectors, basically the z-axis, basically the k component, the ijk component, right? So in this and that is why we basically talk about vectors in P3 syllabus in terms of 3D vectors. So the 3D vectors, as opposed to the 2D vectors you've done in O levels, deals with 3 dimensions. For example, the vector AB will no longer be denoted by 2 5, rather it's going to be denoted by 2 5, let's say -9. This basically implies in order to go from A to B, you need to go 2 units to the right, 5 units upwards, and -9 units inside the screen, for example. All right. But again, these axes, X, Y, and Z, are in our example set arbitrarily, meaning these vary from situation to situation. I mean, for example, in some questions or some situations, this might be the x-axis, this might be the y-axis, this might be the z-axis. In other cases, this might be the y-axis, this might be the x-axis, this might be, again, the z-axis. So you don't really have to remember or visualize which axis is which, because these are not fixed. However, definitely the first number is x, the second number is y, and the third number is obviously z. So what I want you to realize is you don't need to remember, or you don't have to, whenever we're looking at these numbers, you don't really need to visualize where the vector is going as easily as you had to visualize this, for example. So in 3D vectors, the visualization is not really that important. All you have to remember is just a third number is being added, and you will treat it just like you've been treating the two numbers, the x and the y coordinates in your AS. So this addition of a third z-axis really does not change much in terms of calculation. So when it comes to addition, subtraction, multiplication, just deal with them normally, and there won't be any complications and or complexities involved. So for example, if I know that the vector OA is 2i plus 3j plus 4k, again, I don't need to know what exactly diagrammically where 2i, 3j's, and 4k are. I mean, no one's asking you to draw the diagram. And let's say uh, OB is I plus j negative k, and I ask you to find the vector AB. Again, all you have to do is recall from your knowledge of O levels what you vector subtraction. So oftentimes this may be thought of as AO plus OB. For others, you may think of this as OB minus OA. In any case, what you have to do is simply perform the addition subtractions. So for example, this is negative 2i plus 3j plus 4k, and the OB is I plus j minus k. And how would you do this? Well, simply like terms, just like simple addition and subtraction. This is negative I, this is 4j, and this is 3k. That's it. If you're more comfortable with column vectors, you might want to convert these into column vectors first. For example, if OA is 2, 3, 4, you might want to write it as column vectors as negative 2, negative 3, and negative 4 plus 1, 1, negative 1, and then perform the addition subtraction. So notice how the addition of the third number, the z number, all right, the z coordinate really isn't changing much for me in terms of the mathematical operations. Sure, diagrammically it means that there is a third dimension, the third axis that you'll have to consider. But since none of this is being, is important so far, we really don't have to think of what this third number really does for us. So we'll just treat it just like we treat it just like the way we treated the first two digits. So the same thing applies for multiplications. I mean, let's say I tell you, look, the BC vector is 5 times AB vector. What is the BC vector? Well, you basically multiply 5 with AB. So that's negative 1, 4, and 3, which ultimately, just like in matrices, give you negative 5, 20, and 15, right? So this is what this basically means, all right? So you don't have to really worry about, again, for the millionth time, the z coordinate really won't bring about major change in the way you tackle the problem. So you don't really need to worry about um, any major complexity with the z coordinate. All right, as long as you're okay with these simple operations. Now, but we will take a look at a few diagrams. Some questions do relate to some diagrams, and we will be looking at old P1 questions in order to illustrate how the questions appear involving diagrams, in which case the z coordinate and axis are important. We'll take a look at them, but we'll look at them in a bit. But first, you need to recall a few things, a few terms. For example, the modulus of a vector. So modulus is essentially how long a vector is, basically the length of the vector, right? So in 2D vectors, you learned that the modulus of a vector, let's say modulus of AB, which is denoted by mod AB vector, or simply AB without the vector symbol, is equals to root over of the x coordinate square plus the y coordinate square. However, in 3D vectors, all you have to do, and very simply, is just add the z squared. That's it. So if I give you, look, there is a vector AB 1, 2, 3, which is simply I plus 2j plus 3k. You need to be comfortable with both these forms. And I ask you to find the modulus of AB. All you have to do is follow the old formula, which is x squared plus y squared. Just add the z squared. That's all you have to do. And then put your answer in units. So there you go. Not very complicated in terms of the basic ideas. Now, Another concept that you have to understand very well is the concept of the unit vector, something that you've done uh, in additional math, right? So what exactly is the unit vector? Unit vector is any vector that has a modulus or length of one unit, right? So let's look into a hypothetical situation, an example basically, where a unit vector, where you need to be dealing with unit vectors, right? So I tell you, look, the vector AB is essentially 2, 2, 1, right? And I ask you, look, obviously this vector is not a unit vector, right? Because if you think about it, its modulus is definitely not 1. If you go ahead and calculate it, you'll find that the modulus is not 1, 1 unit or 1 centimeter, any way you think of it. Um, but what if I asked you, look, what what is the unit? What is the unit vector in the direction of AB? Or find me a unit vector in the direction of slash parallel to the vector AB. So this is the question. This is what I'm asking you to find. Diagrammatically, what I'm asking you to find is, look, this is the vector AB, right? I want you to find another vector which is parallel to AB but is 1 unit in length instead of whatever the length of this is, right? So these red arrows are all possible answers. Even a vector that is on AB, as long as it's 1 unit in length, I need to find one of these vectors. And trust me, all of these vectors are the same. I mean, once you calculate 1 unit vector, the this vector is the same as this, is the same as this, is the same as that. The positions are different, but their lengths are 1 unit and their directions are the same. So when a vector has the same length and the same direction as another vector, they're basically the same vector. So what I'm asking you to find me one of these vectors, just one of them. And they are basically, and that will be a unit vector in the direction of AB. So the way to think about this is, well, since I'm looking for a vector in the direction of AB, how about I think of it this way? How about I think of it this way? I know that AB is a certain length long, and I can make use of that length or modulus in finding that unit vector. How? Well, let's first find the modulus of AB. The modulus of AB, basically the length of this line or vector, is essentially root over of 2 squared plus 2 squared plus 1, which is 4 plus 4 plus 1, which is root 9, which is 3 units. So essentially, this right here, this blue arrow right here, the vector AB is 3 units long. So you're telling me that this vector is 3 units long. What if I literally slice this 3 unit vector into exactly 3 equal parts? Sorry. So we have one arrow over here, one red arrow over here, the second red arrow of equal length, and the third red arrow. I hope you realize by now that each of these 3 red arrows is 1 unit in length. So this is 1 unit in length, this is 1 unit in length, this is another unit in length. Together, they give you the 3 units as expected, as found, of the modulus AB, of the vector AB. What that means is, if I take this vector notation, these numbers of AB, right? So the numbers in AB are 2, 2, and 1. And if I divide this entire vector in three parts numerically as well, just like I've done it diagrammically, basically divide the 2 by 3, divide this 2 by 3, divide this 1 by 3. What I get is 2 by 3i plus 2 by 3j plus 1 by 3k. This right here is AB vector sliced in three equal parts. And this can be thought of as a unit vector in the direction of AB. If you don't believe me, well, let's calculate the modulus of this newfound vector. The modulus should be 1. If I'm correct, the modulus should be 1. So that's 2 by 3 whole square, 2 by 3 whole square again, and 1 by 3 whole square. And that leads to 4 by 9 plus 4 by 9 plus 1 by 9, which is 9 by 9 square root, which is 1 unit. And how do we ensure the direction? Well, remember that when two vectors are parallel, one vector is a multiple of another vector. So as long as my unit vector is some multiple of the main vector, we know they're sharing the same direction. So look at the blue AB and look at the red unit vector. They shared the same multiple, and the multiple is 1/3, right? So not only did I find my unit vector, I found the unit vector that is in the direction of AB. So hopefully, now bringing all of this together, I mean, in case you're worried about what really happened, what basically what I did is I looked at the vector I needed to find the unit vector in the direction of. I sliced it into, I divided it by the number, by its modulus, so that each vector, each slice, each division is exactly 1 unit, right? And then I applied that rule to the original vector. So all of this boils down to a basic formula, maybe you're familiar with. Unit vector in the direction of, let's say, AB is essentially the vector AB divided by the modulus of AB. That way you find the unit vector which is parallel or in the direction of AB. So for most of you, this is old stuff, but in case um, you're still hazy about the idea, this is how it goes. You take the vector, you find out how long it is. Let's say it's 9 units. You divide it by 9 so that you get 9 equal parts, and each part is 1 unit, right? So you get the unit vector, just like here. All right. So notice again how the third dimension, the z-axis, the k component, really isn't being any different from the other components. So the addition of the third dimension really does not change much. Okay. So that was the old stuff. We we are comfortable with addition, subtraction of vectors. We're comfortable with um, multiplication, scalar multiplication. We're comfortable with modulus, and we've just figured out what to do with unit vectors. Now, let's end the lecture by looking at another example of unit vector where the unit vector is not the final answer of the question, rather it's a stepping stone to solving a question, right? So for example, I tell you, look, the vector AB, so this is another example, the vector AB is 2, 2, 1, and the vector CD is parallel to AB, but, or and, is 20 units in length. in length. Find the vector CD. So maybe you've dealt with these kind of questions again in ADMAT. But what this essentially is asking, look, AB is this tiny little guy over here, right? Which we saw to be of exactly 3 units in length. And then there's another guy CD, which is parallel to AB, but 20 units in length. How do you find the vector CD? Well, since you know AB, the idea is this. The way to approach is this. Using your knowledge of unit vector, find the unit vector parallel to AB, right? Find this tiny little arrow over here, right? The blue arrow, the unit vector in the direction of AB. Since AB and CD share the same direction, the blue arrow, the blue unit vector will also be common for them, right? So we'll find the vector, unit vector of AB, multiply it with 20 so that we can find the vector which is 20 times longer. In our case, that vector comes out to be CD, right? So hopefully that makes sense. So let's go ahead and do that. We just found out that the modulus of AB was 3 units, and that means the unit vector in the direction of AB, let's give it a name, AB cap, is 2 by 3, 2 by 3, 1 by 3. This is that blue arrow over here. It's a double-headed arrow, but I basically wanted to uh, show this as a single arrow. So this is a single arrow over here, which is exactly 1 unit in length. Now, this single arrow may be thought of as being here as well, because they're in the same direction, right? It's and the only difference is, if AB unit vector is this, we can definitely say, look, CD is essentially just 20 of these blue arrows, because one of these arrows is 1 unit, and CD vector is essentially just 20 of these arrows. And because they're parallel to AB, both AB and CD are parallel to each other, all I have to do is multiply 20 to this. And the answer is 40 by 3, 40 by 3 again, and 20 by 3. This, or in the form of IJK, in any way you can write. So this was sort of a review of the old stuff that you did in ADMAT. So you might be bored by now, but let me tell you that in the next lectures, we'll be talking about the new stuff. You'll be talking about things called dot product of vectors. We'll be talking about angle between vectors, right? And finally, we'll be talking about 3D diagrams. And so these were stuff from the old P1 syllabus, which is now incorporated in your P3 syllabus. And then we'll talk about the exclusive P3 stuff, something called the vector equation of a line. And then we'll talk about point of intersection using vector equations. We'll be talking about distance of a particular point from a vector, and more to come in the later videos. But these were always the P3 stuff. All right. And the concept of planes, right? Three-dimensional planes have been discarded, have been eliminated from your P3 syllabus. So these are what we'll be talking about in the upcoming lectures. And the idea of this lecture was to sort of to give you a review of uh, a bit of your, you know, additional math and math D stuff, and but more importantly, to give you an introduction of the third dimension. Very often students freak out by looking at the third number, the z axis, the z coordinate, the k component, right? The ijk component, and they get the idea that by adding this z axis or the k component, there's going to be massive change in how we deal with these stuff. Well, the point of this lecture was also to show you we deal with the z coordinate just like we deal with the other x and y coordinates. So I hope you've noticed by now how I've applied the same mathematical operations to the z coordinate as if it was just like the x and y coordinate, right? So, and we'll be talking about all these concepts in three dimensions with the z coordinate, z axis, and the k component. It's the same thing, and we'll be talking about these things in three dimensions. All right. So by now, get used to the third dimension, the z axis coming in, the k component with the ij as well. So get used to that, all right, and realize that the new number, the new z coordinate really isn't big of a deal. Thank you very much.